Welcome back to our second geometry lesson. I'm Mr. Gass, your friendly guide for geometry. In this upcoming video, we are going to prove three theorems. The first theorem is from 24.1, and the second two theorems are from 24.2. Before we begin, two quick notes. One is, if you haven't watched the first video that is about the terms that we use in circles and their definitions, then you're going to want to watch that because we're going to be using all of those terms, and we're going to want to make sure that we know exactly what their definitions are as we use them. The second note is you're going to want to have a piece of paper and a pencil to make your own notes. You might also want to have a ruler if you like making perfectly straight lines. Okay, without further ado, let's talk about our very first theorem that has to do with circles, and that comes from 24.1. And we're going to use this Desmos app to demonstrate that a tangent is perpendicular to the radius at the point of tangency. The first thing that we're going to talk about is that any points on the interior of the circle are going to be less than a radius away from the boundary of the circle. Now this circle has a radius of 2, so everything here on this green boundary is 2 units away from the center O. Everything on the interior is less than 2 units, and everything on the exterior, all exterior points of the circle, are more than 2 units away. I think that makes a little bit of sense. One thing that we want to remember is that the shortest distance from a point to a line is the segment that is drawn perpendicularly from that point to the line. We're going to use that in this proof. So what we're going to do is I'm just going to animate this a little bit, and we're going to see that any point, no matter where A is, any point along this purple line has a distance that's more than 2 units away. As I get closer to the point of tangency, that single point of intersection that a tangent line has with a circle, as we get closer to that point of tangency, you'll notice that the distance OA is getting closer and closer and closer to 2. And as we, in fact, touch the point of tangency, as we reach that point of tangency, right there, boom, got it, you'll notice that at the point of tangency, that is a distance 2 away. And that makes sense because that point of tangency is exactly the point on the line that is also on the circle. So it would have to be a distance 2 away. Now we have to do a little bit of logical thinking here. Does it make sense for a point on the tangent line to be closer than 2 units away from O? And the answer to that, if you think about it for a second, would be no, because if there was a point on the tangent line that was less than 2 units away, then it would have to be on the interior of the circle. And we know that the tangent line doesn't go to the interior circle, it only intersects on the circle. So the closest the tangent line gets to the center of the circle is at that point of tangency. So that must mean that this angle here is a right angle. And now we're going to switch to the two theorems from section 24.2 after a brief little edit. Here we go. And we're back. So we are now going to tackle two more theorems that come from the beginning of section 24.2. The first theorem comes from the conjecture that if a radius or diameter is perpendicular to the chord, that means it bisects the chord. And vice versa. If the radius and diameter bisects the chord, then it has to be perpendicular to that chord as well. I'm going to prove the first part of that if we start off with a radius that's perpendicular, that means it is a bisector of the chord. And you are going to try to prove the other way. That is, if the radius bisects the chord, then that means it is perpendicular to the chord. So what I've done here is on my circle, I've started off with a chord AB, And I've started off with a radius here, OC, and that radius is perpendicular to the chord. And my goal is I want to show that it bisects the chord. I'm going to use a technique that comes in really handy a lot of the time when we're working with circles. And when we're working with circles, we're going to rely a lot on our knowledge of working with triangles, specifically isosceles triangles and right triangles. And the reason we're going to look at those is because it's very easy to make an isosceles triangle with a circle, because if I draw in a radius here, OB, and I draw in another radius here, OA, then OB and OA are automatically the same length because they're both radii. So OA and OB are both the same length because they are radii. OA and OB are congruent, and that's because they are radii. So you can see that what we've started this proof off with is we've started with an isosceles triangle, OAB. And what we're now going to see is, okay, we can use everything that we know about isosceles triangles and use that to prove something about this chord in this circle. You might recall that if an altitude, here is our altitude, OD, starts from the vertex angle of the isosceles triangle, then not only is it an altitude, but it's a perpendicular bisector. That came from a couple sections back. If you don't recall that fact, that's okay. What we can also do here is we can say that OD is congruent to itself. OD is congruent to OD. That's the reflexive property, our favorite. And then looking at these two triangles, triangle happy face and triangle star, triangle AOD and BOD are both right triangles, so that means we can use HL. So we can say that triangle AOD is congruent to triangle BOD, and that's by HL. And that means, that's right, by CPCTC, AD is congruent to BD by CPCTC, which is CPCTC, which is exactly what we wanted to prove, that if we started off with a perpendicular to the chord, that meant that we bisected the chord AB. So we are done with that proof. You're going to try to see what the proof would look like if we started off with OC bisecting AB. See if you can prove that that means that OC had to be perpendicular to AB. Prove the other direction of the if and only if. Now we're going to prove the second theorem from this section, that chords of equal length are equidistant from the center of the circle. So I've started off here by drawing two chords, AB and CD. Again, this is an if and only if. Remember, if I write the word are, then that's really an if and only if. Chords are equal length if and only if they're equidistant from the center. So I'm going to again prove one part of this, and you're going to prove the other part. I'm going to prove that these chords that are equal length are equidistant from the center. And you're going to prove that if they are equidistant from the center, then that means the chords are equal length. So here we go. I'm going to say that these two chords have the same length. Let's say they have length 2x. So the length of AB and CD is 2x. Then what I'm going to do is I'm going to find the midpoint of each segment. The midpoint of each chord is here. We'll call that point E. And here is point F. Those are midpoints of those two chords. So X and X, X and X. And now what we're going to do is we are going to try to show that that means that the distance from O to E is the same as the distance from O to F. We want to show those two distances are the same. So we're just going to start by doing the same technique as we did before. We're going to draw in a radius. OA, there's a radius OA. That's going to have length R. And we're going to draw in OC. That's also going to have length R. And then we're going to draw in the segment that goes to the midpoint. Now, what do we know about OE, this segment that goes to the midpoint, and I actually drew it all the way to the edge of the circle? Well, from our earlier theorem, we know that if it goes through the midpoint, that must mean that it's perpendicular. That's what you proved when you proved this first theorem in the reverse direction. So if it went through the midpoint, that must mean it's perpendicular. Let's do the same thing here with OF. With OF, I'm going to draw in that line, that segment. And again, OF is a radius that goes through the midpoint of CD. So again, by the theorem we had above, we know that's perpendicular. So what we're looking at here is we're looking at two right triangles. So let's write that here. So we know that AOE and COF are right triangles. Well, if they're right triangles, that means the Pythagorean theorem must work for them, right? And if I look at AOE and COF, will they have the same length hypotenuse? They have a leg that's X and a leg that's X. So that must mean that this missing leg OE and this missing leg OF, they both have to be the same for the Pythagorean theorem to work. So that's what we're going to say. We're going to say that OE has to be the same as OF, and that's because of the Pythagorean theorem. And that's what we wanted to prove. We wanted to prove that these two chords, AB and CD, because they were the same length, that meant that they had to be the same distance from the center of the circle. And we're done with our proof. And you are going to prove the opposite, that if the two chords started off equidistant from the center, so if we knew OE and OF, if we knew that distance, would that necessarily mean that these two chords were the same length. You're going to prove that direction. Thank you for watching, and we will catch up with the rest of 24.2 and 24.3 in the next video. Take care.